All right, welcome back to AI for Cybersecurity. I hope you're enjoying the show so far. Our next speaker is Mark Sherman. He is Director, Cybersecurity Foundations at CERT, Software Engineering Institute at Carnegie Mellon University. Please join me in welcoming him to our virtual stage.
Thank you. Let me get set up here. Excellent. Welcome, everybody, to the session on Introduction to Recognizing Deepfakes. So we'll just give a brief introduction about what organization we're with and how this fits in to our larger mission. And then we'll dive right into how deepfakes are made, and then give you some ideas about how you might recognize deepfakes, sort of as, if you'd like, as a layman. But it'll also give you some insight as to how researchers are building new kinds of detectors that use basically the mathematics of creating deepfakes in a way to recognize when those deepfakes actually appear. So just to give a little bit of background, I am part of Software Engineering Institute within Carnegie Mellon University. If you're not familiar with Carnegie Mellon, we have a lot of academic depth in pretty much every area of computer science. And in particular, within the larger Carnegie Mellon University is the Software Engineering Institute, which is a research organization that the Department of Defense founded back a while ago in 1984. And we focus on software engineering, cybersecurity, and artificial intelligence. And deepfakes actually is the intersection of all three of those. The CERT division, which is what I'm a part of, I'm a director within the CERT division, focuses particularly on cybersecurity and deepfakes. In fact, all sorts of dis, and misinformation is becoming a more important issue in securing our environment and maintaining our national security. So how does one go about creating deepfakes? Well, historically, a lot of false videos and images were made with things like Photoshop. And frankly, that is still probably the largest technology used for creating things, just like Excel is probably the most used database technology out there. But it has its limitations. It doesn't have a lot of high fidelity. And as people wanted to get better and better fakes, sometimes for legitimate purposes like creating training or marketing materials, but sometimes for not so legitimate purposes, they've turned to various kinds of machine learning techniques in order to build these kinds of deep fakes. There are several of them. Perhaps the most popular one is autoencoders, and that's the one we're going to talk about here. The way autoencoders work, as you see here, it first takes an original face. So take my face, take lots of different versions of my face, train a machine learning system called the encoder here, and it creates sort of a description of my face, how far apart my eyes are, how my lips move relative to my eyes and my nose, and so on. And it creates, if you like, an abstract description of my face, or whatever face that gets fit into that. The second part, called a decoder, takes that abstract version of what my face is doing, that my eyebrows are up or my mouth is down or what have you, and automatically reconstructs my picture from that. So from an abstract view of some eyes and a mouth that's turning down, it creates a picture of me with eyes and a mouth turning down. When you put these together, you wind up with something called an autoencoder that learns my face, takes it apart into various abstractions, then can reconstruct it and come back with my face again. Now, of course, we could do this with more than one face. I did it with my face. I could do it with your face as well. And again, I can create something that will abstract out your particular features. From those abstract features, then train a system that can automatically reconstruct your picture from those features. Now, the secret sauce, if you like, of autoencoders is that they use that same encoder, that same piece of machine learning that's abstracting the various pieces of our faces to be the same. So we train it on both my face and your face. And as a result, it has abstracted out our common view, our common attributes. And from those common attributes, if I use the decoder on top, I get a picture of me. If I use the decoder on the bottom, I get a picture of you. How does that work then in creating a deep fake? Well, I'm probably jumping ahead. You probably already recognize this. You take my face, so I have my eyebrows going up. I feed it into this shared encoder. It comes out with an abstract version of me. But then I feed that into the picture generator, the decoder for you. And now we have a picture of you with your eyebrows going up. And so that's the process by which the deep fakes are made. So understanding that, what might be able to do in order to look to detect how deep fakes are found? Well, I would say without going into math, you can just do some visual detection techniques from deep fakes. And some artifacts can be detected just by looking at them. One is mismatched skin tone at borders, especially for face swap. Now, I sort of waved my hands about taking a picture of me and taking a picture of you and so on. Building these encoders and decoders is very expensive. So a high-end machine learning application has what's called over 1 billion hyperparameters. The insides of machine learning, we're not going to go into them here, but require lots of different interacting pieces. And they require, each one of them has a particular setting as to how they interact with each other. The training process, and you may have heard about that from machine learning, is all about picking the right values for each of those different pieces. To give you a feel, we have 1 billion of those kinds of parameters. It literally takes CPU centuries to train, millions of dollars. It's very expensive to have a big one of these. So instead, many times when doing deep fakes, they only concentrate on a small piece, the face. When you do that, you wind up with inconsistencies as my face gets put on sort of other different surrounding part of the head. And as a result, you see these border mismatches. You can see similarly inconsistent light sources and shadows. Again, from the issue about having to take only pieces of it and reconstruct the fake for only pieces of it, some piece may have a very bright side coming on one side, one may have a very dark side coming on the other side. No, I'm not a deep fake that happens to be the lighting of my office. But if you see different light sources and shadows, you see a shadow of a nose coming down, you see a shadow of glasses going up, then that's an indication that there's a deep fake. Similarly, you can recognize certain kinds of sounds. You know, B's and P's have pursing of the lips. You don't see that, but you hear that. You obviously have a mismatch between the sounds and what you're seeing, and that's another indication of deep fakes. Discontinuity is another example where something is happening, and as the deep fake gets created, it gets created in chunks, and all of a sudden one chunk gets created, and then you see a different chunk, and someone has moved, or their face has jumped from one kind of feature or expression to another. That discontinuity is an indication of a potential deep fake. People blink their eyes in certain kinds of patterns. If you see those kinds of things changing, and again, that's something that you can observe, then that's another example that you might see indication of deep fake. Something even as simple as mismatched jewelry. I have different earrings on, or whoever you're looking at has different mismatched earrings, or one's up and one's down, or you have a watch in one place and don't in another place. Those kinds of telltales also are suggestion of deep fakes. And finally, given some of the technology, we're going to take a little bit more about some of the mathematics here in a moment. You could have what are called selectively indistinct features. As the decoders try to recreate the face, at various points, it uses techniques in order to fill in pieces it doesn't know. Remember, it comes in with these abstracts, my eyes are up, or my eyebrows are up, and my mouth is down, and from that recreates the face. Having done that, sometimes some places of the face will be in very sharp focus. Other parts of the face may be very out of focus, fuzzy. If you see something like a very fuzzy nose, but a very crisp in focus eyes, that again is a telltale sign that you may be looking at a deep fake. So that's, if you like, some human variable ways to do that. I have to admit, there have been some studies which showed that even understanding these things can sometimes make it hard to look for deep fakes. Some people are better at it with others. Frankly, the research is not very conclusive as to whether people can actually be trained to recognize this or not. Some people are very good at it. Some people just don't seem to be able to catch these kinds of things. Let's talk about some of the mechanical ways. So what are the scientists, the data scientists doing to work here? Well, they are exploiting some of the mathematical artifacts that come about from using this kind of technology. The particular thing that we're talking about here with the autoencoders is called GAN technology, and it typically leaves some unusual kinds of features sort of at the very micro level. In particular, it tends to leave a checkerboard pattern because it does something called upsampler and interpolation. That's another more fancy way of saying what I was saying before was it takes your notion that your eyebrows are going up, but then it has to fill in a lot of the details. The way the mathematics works to recreate the image is that it winds up generating a checkerboard pattern. And you can see an example of a checkerboard pattern in this particular image. And if you look at that in what's called the frequency spectrum, again, taking a Fourier transform, but it's another way to look at the image rather than looking at the pixel image, you can actually detect this checkerboard pattern and say, that is obviously a deep fake. So that's the residuals that you see. Another way goes back to the very original idea of how these were created to begin with. So recall that we had these encoders and decoders, and we've now been talking about how one could take my encoder and then use your decoder. But given that this technology leaves certain kinds of mathematical fingerprints, if I know what that original technology was for the encoders and decoders, I can basically make images of myself. And here they're showing images of a horse. But because, again, it's creating something from an abstraction, not the complete thing, it leaves certain kinds of artifacts. And again, these artifacts are usually in something called the frequency domain, not really very easily visible to the eye, but easily visible when you actually move it into the other kind of analysis. And you can therefore see changes in the image from the original until the generated one. If you take those versions, so make a variety of these original and constructed ones, and you look at the changes, the artifacts that were done, and take those artifacts as input to a new machine learning algorithm, take, to be very flippant for a moment, algorithm that can distinguish between apples and bananas. You take a brand new one and you feed it as input these kinds of patterns that come from the differences between using this pair of technology for generating images of myself again. You can train that system to recognize the artifacts of those particular pairs. And therefore, if you start feeding in potentially fake images into this new machine learning system, it will recognize the presence of these artifacts and say, aha, I recognize this as a fake made by this kind of system. And you might ask, well, how am I going to find one of these kinds of systems? Recall earlier that I mentioned how expensive it is to build one of these things. It turns out there's actually only a few number of core technologies that people start with. And they use a technique called transfer learning, and that's the subject of another talk. But using that technique, you basically take something that's already there and you slightly modify it to build the one that you want. The consequence is that many of these things all have the same parentage, all have the same lineage. So it's very likely that you can find what the original one was by a very modest amount of mathematical detective work. And therefore, you can really do create the the autoencoders that are used in order to do this, and therefore generate these images. The last thing I'd like to point out is that sometimes you can look for physiological inconsistencies at the machine level. We talked about the lips and the sound, same thing with sound and other kinds of facial movements that are going on. Between facial movements and respiration, machines can actually watch videos of your face and tell when you're breathing. They can tell your heartbeat. If all of a sudden your heart jumps and starts racing and then starts coming down again, that's a telltale sign of that's something of a deep fake. And you also have to worry about something that are scale differences. Again, very broadly, you say, I have eyes and I have a mouth, but then it's got to fill in all the details. That doesn't always happen consistently. And in this picture here, there's a sequence of pictures, and you see her hair color change even though it's the same hair that's being looked at. And that's because it got interpolated differently in different frames of the video. And then telltale sign of an inconsistency. We've only touched the surface here. There are lots of proposed ways to build deep fakes. The challenge is that as fast as you can figure out a way to detect it, the people building them can figure out a way to get around them. I talked about these telltale mathematical signs. You could post-process some of that to get rid of them. So instead, the current research is, how do you take multiple of these and use them together? Because it's very hard to fool them all at the same time. Every time you do some post-processing to fix something, it leaves a trail in another area. If you'd like to learn more, get some basic information, by all means, there's a nice article that we just published about deepfakes, and you can learn how to make and detect a deepfake. Thank you again for coming. Happy to take your questions, and have a great rest of the conference.
Amazing, Mark. Thank you so much. If you could stop sharing your screen, I know this virtual audience wants to give you a huge virtual round of applause. Thank you again for these incredible insights today. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.